In this video, we're going to be talking about section 1.2, which we're going to break into two parts. And today we're going to just kind of talk about the basics of functions. All of this should be review. I will say I do have a bit of a cold setting in, so you might hear me do that a couple of times. It's going to be annoying. I apologize. A function f. So definition of a function. A function, we'll call it f, from a set A to set B is a relation that assigns each element of x in set A exactly one element in set B. All right, that is a very formal sounding definition that you might have to read about 14 times before you really see what's going on. But really, all this is saying is you've got these numbers in set A, which I'll represent with this circle, and then you've got some numbers over here in set B. So what a relation is it's any sort of connection between the numbers in A to the numbers in B. So we've got a relationship between A and B. A function is a specific relation where when you have one number over here, it maps to exactly one number over here. Let's say 8. So 4 goes only to 8. So a member of the domain of A goes to a number 8, which we're going to be called the range. So this is the range. These are the outputs. This is the domain. These are the inputs. So 4 goes to 8 and only to 8. So if each number over here, whatever you have, only goes to one place, then what you have is a function. So for example, if 2 goes to 8, that's fine. 4 can go to 8, 2 can go to 8, everything can go to 8. But 2 cannot go to two places. If 2 leads to an 8 and to a 1, then you don't have a function. So again, think about this in terms of inputs and outputs. You plug a number in and solve for y, you should get only one possible number. If you get two numbers, then that would not be a function. Most of what we work with are functions. Okay, so example number 1, testing for functions. So we have some relations here, and what we want to do is just kind of take a look and figure out if they are, in fact, functions or not. And really what you're looking for is simply, is your input listed more than once? If it is, especially when it's in a table, we see that 2 is going to 11, but 2 is also going to 10. 3 only goes one place, 4, 5 only goes one place. Those all happen once, so that's fine. But the fact that we have at least one spot where the domain has two different numbers in the range, then that would not be a function. If we listed that in a mapping diagram, then what we have is our domain, and we have our range. And we list the numbers we see in the domain. In this case, I see a 2. I see another 2, but I'm not going to write it twice. I'm just making a list of the sort of like the ingredients I have. I've got 2s, I've got 3s, 4s, and 5s. And over in the range, I'll go smallest to biggest. I have 1s, I have 5s, I need an 8, I need a 10, and 11. And then we just map. 2, it says, goes to 11. That's just like saying we have the point 2, 11. But 2 also goes, as we see, to 10. So that's like the point 2, 10. And so 2 goes to two places, to 11 and to 10, and it's therefore not a function. You can also demonstrate a relation or a function graphically. And looking at it graphically, what we see is there's 1, 2, 3, 5 distinct points, which could have been written as a table, which could have been written as a mapping diagram, which could have been listed as individual points. They all convey the same information. And so what we're looking for here is 2 points lined up vertically. So for example, if I was to graph the point 211 and 210, not to scale here, so 211 would be like right up here, and 210 would be like right here. And those numbers are lined up vertically. And so the test that we do, especially if you have a graph, is you do what's called the vertical line test, the VLT. We pass a vertical line across our graph. We grab this line and then we just slide it over. And if at any point it hits 2 points at the same time, then we don't have a function. And you can clearly see here that we are fine. This is a function because each input has only one output. All right, let's keep moving. Example number 2. Determine whether each relation is a function graphically, and we'll also think about it algebraically. All right, so let's think about graphing these. Let's do B first. Quick inspection on B. Hopefully you see that this is a quadratic. This is a parabola. If we try to make it say y equals, because that's how we're most comfortable graphing things, I get negative y equals negative x squared plus 3. I get y equals multiplied by negative x squared minus 3. So my hope is that we can all look at this right now and remember exactly what it looks like. It is a parabola that has shifted down 3 units from its standard. And we're going to review all this, I believe, next section. So we've moved everything down 3, and then the pattern is it goes up 1, 3, 5 to form our parabola. 1, 2, 3, 4. Oh, I guessed. No, I was right. All right. So quite clearly, if we pass a vertical line over this, we're only going to hit 1 point for each x value. So graphically speaking, yep, this is a function. And if you wanted to like provide evidence, like how are you guessing, like why do we know it's a function? We could say, yes, it's a function because it passes the vertical line test. All right. All right, let's back up and take a look at A. To graph A, I'm sort of at a loss unless I'm going to do one of two things. Make a table of values or rearrange it so that it says y equals. If your Algebra 2 class got far enough last year, you might have studied what's called conic sections. And so you might recognize this as a circle. If you don't, it's okay. A table of values gets us there anyway. But let's go ahead and solve it for y. So I get y squared equals, I'll say 9 minus x squared. And then I'm going to take the square root of both sides. And let's talk about square roots a little bit. Since we're the one that has to introduce the square root to solve this problem, I've got to put the square root here to cancel out the square. Then I need to be responsible for both the positive and the negative answer. Okay, so anytime you have to include a square root yourself to solve a problem, you have to make sure you consider the positive and the negative. So once we're here, if we make a table of values, we can kind of quickly see, and maybe not so quickly, but we might notice very soon that there's only a limited numbers I can plug in. In fact, if I plug anything less than negative 3, when I square 3, I get 9. 9 minus 9 is 0. So anything lower than negative 3 is going to lead to undefined. And negative 3 leads to a 0. When I plug in, let's just go to 0, I get the square root of 9, which is 3, but I get a positive 3, and I get a negative 3. And that sort of gives away the whole ball game right there, that when I put an input of 0, I get 2 different answers. So if for nothing else, we know that this is not a function. Graphically speaking, this is a circle. Excuse the crappy graph. Centered at 0, 0 with a radius of 3. 1, 2, 3, 3, 3, 3. And so we can clearly see that it fails the vertical line test. So even if you weren't 100% sure what it looks like and you just sort of started plugging numbers in, as soon as you plugged in something that returned 2 answers, then we have our answer. All right, let's continue and try solving the next one. When in doubt, set things equal to y and see what happens. So in this case, I've got two y values. So we've got two choices, and legitimately, a lot of you might take the wrong choice. And the wrong choice is just to kind of give up. The right choice is, if you don't know what's going on, just try something. Just try manipulating this thing with legitimate math until maybe you get some inspiration. So when I'm faced with a question like this, I, having a fraction seems like it's muddying the waters a little bit. So I'm going to multiply both sides of this problem by y. And then I get xy equals 3 minus y. So that's better, but now I'm a little confused because I have two y's. So honestly, there's a lot of things we could try, and I'm gonna show a few and then probably erase them. Um, some kids might say, "Well, let's divide by y." Well, if I divide by y, well, guess what? I just undid what I did a second ago, and I'm going to be right back where I started. So that doesn't seem like a good idea. I see some kids in this situation say, "Well, let's divide by x to get y by itself." The problem there is we still have two y values. So that's really confusing and not very helpful. And so then what I would hope eventually you might recognize, and maybe this is a long shot at this early in the year, but the one problem solving strategy that I like to follow is basically, if you're confused, make the problem easier. We're faced all the time with solving equations that have multiple of the variable we're interested in. As an example, I'm just going to rewrite this question real quick. I'm going to think of this question as like 2y instead of xy. 2y equals 3 minus y. Now, if I asked you that question, I'm pretty confident we would all get a pretty good answer here. And what would we do? We would add y to both sides, giving me 2y plus y equals 3. So I had two separate locations where there were y's on opposite sides, and now they're on the same side. Then what do? I do 2y plus y, which is 3y. But what am I really doing there? I'm basically saying, hey, they're the same kind of term. So ignore the y and add the coefficients together, right? I'm basically saying this. Let's ignore the y and let's just add 2 plus 1 together. And then let's stick a y on it. Well, congratulations. That's just factoring, right? You factored the y out of both terms. Here it is, leaving you with a 2 plus 1, which is 3y. That's how we add terms together. So I would say, like, it seems like it's working okay here, right? I got 3y equals 3 and divide, and we're done. Well, let's come over here. Let's add y to both sides. Xy plus y equals 3. And now I can't add those together because they're not the same, at least, not in traditional sense. But what I can do is factor out the y, which leaves me an x plus a 1 times y equals 3. And then, just like over here, when I divide by 3, I'm done. Here, instead of dividing by 3, I'm going to divide by x plus 1. I'm going to erase this so I have room. So that was going to leave me with y equals 3 over x plus 1. Okay, now you might be sitting here like, okay, great, but I don't know how to graph that. Well, hopefully you remember, hopefully there's not many of you, but this is a rational function. And again, when you're faced with how to graph something and you don't remember the shortcut, then you just fall back on table of values. Eventually, you would arrive at a graph that, if you remember, is a version of y equals 1 over x, which quickly looks like this. And we're going to shift it 1 to the left. So this is a graph with a vertical asymptote, at -1, a horizontal asymptote at 0. And then we don't need to be too specific because we're going to review these in detail. But then the graph of this follows the asymptotes and looks like this. Short version is At no point do we see an x value lead to two different y values. And so this is definitely a function. All right. Now we talk about this algebraically. And the good news is we've already done all the algebra to support us. So, for example, we've looked at pictures to answer these questions, but the algebra of it is right here. We rearranged this and solved it for y, and in the process of doing so, what did we create? We created this positive and this negative. Well, by definition, what that's saying is when you plug in a number, you're going to get the positive version and you're going to get the negative version. So that tells us algebraically right now that one input is going to lead to more than one output. And so therefore, we've already shown this algebraically. This one we rearranged for y. And once again, if we think about it logically, I plug in an x value. There's no way to get two y values out of this. I'm only going to get one answer. You plug in an x, you're going to get a single y. And so that we have shown algebraically as well. And the same is true with part C. We rearrange the equation to here. And once again, even if you're not positive what this graph looks like, you can clearly see through trial and error, plug in a number, you get one answer. There's no way, there's nothing in there. The only issue would be is if you tried to plug in -1 and then there's no answer, right? But that's not an issue for functions. The issue is, do you get more than one answer? And so everywhere else is just going to give you one single answer. So we're good. Okay, let's keep going. Hopefully I haven't lost you. Quick pause to talk about the word discrete versus continuous. When you're talking about sets of numbers, you could either talk about discrete numbers, and that would be individual numbers. So for example, we were counting people in the room, right? There's either 1, 2, 3, 4. There's not going to be decimals. There's not going to be anything in between. It is, individual numbers. Continuous numbers is when we are thinking about all the numbers, including all of the ones in between them. So, quick thought of that would be, thinking about time. Time, not only do you have 1 minute and 2 minutes and 3 minutes, but you have all the time in between. So as we go from 9:05 to 9:10, we're going to hit every time in between, right? So, so that's discrete. Basically, think of that as individual numbers. And continuous would be, I hate using the definition, the name in the definition, but continuous is exactly that. It is not individual numbers, but it is a range of numbers. So everything in between sets of numbers or two different numbers. Okay. Now, when we're talking about sets, generally speaking, when you're going to list a bunch of numbers, you're supposed to use what's known as a brace. So if I was going to say, "Hey, let's list all of the day of the month that your birthday is," right? So we could start making a list, and as I made the list, what I would do is I would have a brace. So this brace or a squiggly bracket, this is where we would now document those individual discrete numbers. Oh, you said you've got a 2. Oh, you were born on the 5th. Oh, you were born on the 6th, right? We list them individually. So the way we do that is with these guys right here known as braces. Okay. So if asked for the domain of a problem like we started with, where there was just individual numbers, we would say, hey, the domain are these numbers. But when we're talking about a continuous set of numbers, then we're going to talk about the numbers starting and ending, right? So if we wanted to say all the numbers between 0 and 10, then what we would talk about is we'd start at 0, and then we would just say, hey, go all the way to 10. And we would have to decide what kind of, or whether or not we're including the endpoints or not. So if you want to include the endpoint, you would use a squared off bracket. Also I think of, and I don't really honestly remember where this language comes from, but I think of that's called like a hard bracket. That's you'll hear me say that at least. Honestly, don't know how formal that is. And then you'll see me if I don't want to include the endpoint, like a 0. So 0 is not included, but 10 is. Then I would use what's known as a soft bracket or parentheses. Okay. So that's equivalent to me saying all of the x's less than or equal to 10. Notice the or equal is because of the squared off bracket, but greater than 0. And you'll notice I don't have the or equal to here because I have the parentheses. So those two things mean the same thing, but it's just so much easier to write it in what we would call interval notation. And we're going to practice that in just a minute. Okay. So let's take a look at example 3. Here we have what I am claiming are 3 functions, and a quick vertical line test will verify that. And what I want you to do is practice your interval notation. And let's talk about the domain. So when we're talking about the domain, we're talking about what x values are used or have been used or could be used in this problem. So the message that we're getting across here, I'm going to turn off my graph lines here, is that we're starting at -3. And because we have a solid dot right here, not an open circle, we know that that point is included. So my domain is simply going to be from -3, including it, all the way to, and it looks like I'm indicating we just keep going. And so that means we're going to go to infinity. Since we can't say a specific number, what infinity is, like we're not saying go up to 1,000,000, we're saying just keep on going. Infinity is always with an open bracket or a soft bracket. Okay, open and closed, hard and soft are ways you'll hear me talk about this. Okay, this one we would call open, and this one we would call closed. So that is the domain. If we were going to use formal language, we would include a couple of things. And at the very least, we probably ought to do one little thing to make this better. I'm going to include a symbol here. So domain are x values, right? So if I'm answering what the domain is, the better answer I should have done is we're talking about x values. And now we define the x values. So all of the x's, and then this symbol right here, this colon, is the word such that. All the x's such that x's, so the x is in question, and then we have this symbol right here, which is the symbol is an element of. In other words, I'm about to describe, right? I'm saying, oh, well, the domain are x's. Well, which x's? The x's that belong to the set of numbers -3 all the way to infinity. This would be the best way to answer the question of domain. Now, again, we're all here kind of for different purposes, but the main purpose for most of us is this is not the end of our math journey. We're going to keep going. And so understanding this language would be critical. If this is the end of your math journey, then you can probably get away with the top line just fine, but we need to understand the language of math. And so I'd like you to do your best to use the formal language. And in that case, let's answer about the range. And let's answer it the right way. Ranges are what kind of things? They are y values. Well, what kind of y values? Well, the y values such that they belong to what set of numbers? And we always go from low to high. And despite this thing looking like it's curling up, I'm intending that this is continuing to go down. And so it looks to me that we're going to start at negative infinity because we're going to eventually, all of the numbers down here will be covered. And the biggest number we see is a 2. And the 2 would be included because there's a solid dot here at this point. And so this would be the best way to write the range. All right, why don't you pause the video and try to do B? And let me scroll down and show you C. So there's B and C. Why don't you pause and try to write it out with the formal language? Okay, let's see how we did. So the domain and the range. Okay, domain, we're going to have to be a little tricky because what we want to do is say, well, hopefully we see that again, everything this direction, everything this direction, which almost seems like everything, except I've got this open hole here at 4. At 4, there is no answer, so 4 is not part of my domain. So I'm going to say the domain are all the x's such that those x's belong to the group. And that group is going to start at negative infinity, and it's going to go all the way until we get to 4. But 4 is not included in the group. So 3.99999 is, and we can keep doing that all day, and so we use a soft parentheses and open parentheses here to indicate not including 4. But then we're going to pick things right up and start again and say, but we can also go from 4 to infinity. And then the one symbol we would use is this symbol right here, which is union. And union means basically join the groups together. So we may have written them as two distinct pieces, but the symbol we're about to use glues them together and says, hey, think of this as just one set. And so that symbol is a very handy U for union. It's a very tall, kind of skinny U. It's not going to be just a normal looking lowercase u or anything. That also has the name or, right? We should be familiar with that word because it's saying numbers in here are fine, numbers in here are fine. And the way we say that is you can be in here or here. So this is what union does. It merges them together. Doesn't matter which group they're a part of. They're now just one family, all part of this one group. All right. Range. The lowest number it looks like we have is -2, and that 2 is a y value. So we're saying all the y's that belong to, except that that -2 is not actually there. And we're going to go all the way to infinity. And so that would be our range. All right. Try the domain on this one. And then be careful on the range. Check your range. There's a little misleading piece here. The domain appears to be everything, except for 3. So I'm going to say all the x's such that x belongs to the group negative infinity to 3, open and open, join it with the group 3 to infinity. And the range. Now, your first thought might be to say everything but 2. And honestly, I wouldn't blame you because I've probably made that mistake myself. But why is it a mistake? Well, 2 is not included right here, but it does appear to be included over here because the graph is clearly showing we're above 2 at some point. We were below 2 at some point. And so in order to get from here to here, obviously I had to have a 2. And so even though it's not included at this point, it is included right over here. So y would actually be everything, negative infinity to positive infinity. That's in interval notation. You could also just do the shortcut on this one if it's all real numbers. You could just use the symbol for that set of numbers. So there's an agreed upon symbol for all real numbers, and that is a fancy uppercase R. So the way I make this is I draw a line, and then I draw a capital R over the top of the line. So this R, and that's not my best work. Let me try again. Somewhere in there. That indicates the set of all real numbers. All right, let's keep going. Okay, graph the function and state the domain by analyzing the graph. So once again, hoping very much that you remember enough out of Algebra 2 that you can do these problems without using your calculator. But if you need your calculator, if you know how to use your calculator, go ahead and do that. You can also do it in Desmos if you prefer. But I'm hoping very much that you recognize this is just the parent function, the square root of x, and it's shifted over 3 units to the left. So 1, 2, 3, this graph, and then it's up 1 over 1, up 1 over 1, 2, 3, up 1 over 1, 2, 3, 4, 5. It's our same sideways parabola or pattern that we do for a normal parabola, just flipped upside down. I'm sorry, flipped sideways. Graph the function, state the domain. So based upon this, knowing what I know, I would say the domain would be all the x's such that they belong to the set of numbers starting at -3, including -3, and keeps on going. All right. G of x, I'm hoping very much that you remember the basics of rational functions, but honestly, that's probably the one you remember the least. This is a rational function that's been shifted over 2 units. So we're here. And we've shifted up 3 units. So there's a horizontal and vertical asymptote now intersecting up here at the point 2, 3. And then from there, we just have this point at 1, 1, and I'm just going to fake the rest. Hug the asymptotes. Hug the asymptotes. So if I'm answering the domain, it looks like all numbers are good except one number. And that number, of course, is 2. And we know 2 is not able to be used because 2 minus 2 is 0. And we cannot divide by 0. So we're talking about all x's are fine as long as it doesn't include a 2. So x belongs to the group -infinity all the way to 2, joined with the group 2 to infinity. All right. Now I'm asking you to go back and think about these algebraically. And honestly, this one, it's not hard, but we just got to think about it a little bit. And let's use the math, even though it might be obvious, let's use the math to support us. So if you search your memory, there's only a few things in math that are, not okay. One of those is we cannot take the square root of a negative. And the other is we cannot divide by 0. There are a few others, like logarithms have some issues, and we'll learn some more this year. But short of that, you can pretty much do anything you want with a number and an operation. So what do I really need to do to figure out part A if I didn't know what the graph looked like? I would basically want to say that I need x plus 3, right? This right here, that's where my trouble's going to lie. And what do I need to have true about x plus 3? X plus 3 has to be greater than or equal to 0. Whatever x's make that happen, I'm in shape, right? X plus 3 cannot be a negative, so it has to be bigger than or equal to 0. Solve it, and of course I get x is greater than or equal to -3. So what is that telling us? Any number I use of x that's bigger than or equal to -3 should be fine. And so that is my domain. And that is exactly what the graph shows, right? We start at -3, and we're going this direction. Everything bigger than -3. So then we get to part B, and when we do this one algebraically, I don't have to worry about negatives anymore. Now the question is, well, wait a minute, I can't divide by 0. And so the way I usually approach this is I figure out the thing I can't do, and then I don't do it. So in other words, I know the problem is going to happen when x minus 2 equals 0. And so when is that? And we add 2, of course, to both sides, and I get x equals 2. So I'm not saying the domain is 2. I'm saying 2 is the problem area. And so the domain is everything but that problem area, which is what we said before. So that's what it means to show it algebraically, right? What is the math that's going to work? What's the math that's not going to work? And figure that out. All right, I think we'll get some opportunities to practice this right now. All right, so here are 4 problems. I want you to pause the video. I want you to try to figure out what the domain is by figuring it out. Really, what can't you do, right? Or what can I do? All right, so here we are in part A. Don't have to know what this graph looks like. I know that the problems is going to happen if I try to take the square root of a negative number. And so all I have to do is ask the math a question. Hey, math, when are you going to be greater than or equal to 0? And now I just need to solve this. So I'm going to subtract 9 on both sides. I'm not going to show it. I'm just going to do it. And then I need to get rid of that negative. And so to get rid of a negative, I need to multiply by a -1. And in doing so, since I'm dividing or multiplying by a negative across an inequality, I have to flip the inequality. So I get x squared is less than or equal to 3. And then I take the square root, and I get x has to be less than or equal to, let's see. Wait. I already did the math on that. My apologies. This is a 9. The square root of positive or negative, the square root of 9. Okay. So I get x has to be less than or equal to positive -3. Now, this is a little bit weird. And we probably should formalize the math a little bit here. And I did something a little bit. We should include some absolute values here probably. But long story short, I'm going to interpret this the right way, right? So what is this telling me? This is really saying that these x values, they've got to be between 3 and -3. Because if I get bigger than 3, then I'm going to have a negative number. Okay? So I know we've got to be less than or equal to 3, but technically greater than or equal to -3. And I should have done something fancy with an absolute value there. But I hope what I've just said makes sense enough. And so when I graph this thing, I know I've got to stay between -3 and 3. Because as soon as I pop out and do like a 4, now I've got 9 minus 16, and that's a negative number. And if I go below -4, then that's also going to be 9 minus 16. All right. Part B, I can't divide by 0. So I just need to ask myself, when is 2x minus 3 equal to 0? And that would be add 3 divided by 2 at x. Hello, that was weird. X equals 3/2. And so my domain are all of the x's that belong to the set of numbers that are everything but 3/2. So -infinity to 3/2 and 3/2 to infinity. How would I describe this? I'd say everything but 3/2. I did not write the domain over here, but it's a pretty simple domain. All of the x's that belong to the group that starts at -3 and ends at +3. And the 3's are fine. So they're included. Okay, next one. What can't I do in math? I can't take a square root of a negative, and I can't divide by 0. You'll notice the numerator has none of those things, so I don't care. So now I just have to go down and analyze, what do I care about? I know that I need 6 minus 3x. Because of the square root, I need it to be greater than or equal to 0. But because it's a divided by, I can't actually have it be 0. So all I really care about is when is it greater than 0. So I'm going to subtract 6. And I get -6. And I'm going to divide. And again, I'm dividing by a negative, which flips the inequality. And I get x is less than 2. I don't have any positive negative stuff to deal with because I don't have, I'm not the one taking a square root. It's already there. And actually, that was a silly thing to say. Sorry, my mind is starting to wander a little bit. There wasn't even a square root to deal with here. So x is less than 2 is the answer. And so my domain should be now the x's that belong to the group, starting at negative infinity and going all the way to 2, but it's less than 2, so we're not including it. Pretty easy to check our work on this one because there's likely, depending on how much you remember or how much you're paying attention, we're going to forget to flip that thing sometimes. And so you'll never know you got it wrong if you don't ever stop and think about it. So stopping and thinking is a good idea. I'm saying values less than 2 are good. So I'm going to plug in a number less than 2, like 0, and verify it works. I plug in 0 for x, and I get the square root of 6, no problem. But notice, had you not flipped the inequality, then you would have said the answer has got to be greater than 2. So I plug a number like 10 in, and I get 6 minus 30, and that's not going to work. All right, and then on this one, there are no problem factors. There's no issues. There's no fractions. There's no dividing by 0. There's no square roots. So my domain are all of the x's that belong to negative infinity to positive infinity. Or I could say all the x's that belong to the real numbers. All right. So hopefully that all makes kind of pretty good sense, at least what we're trying to accomplish. I'm not saying every single problem will be easy, but what we're trying to accomplish is pretty straightforward. What's the graph look like? What's being left out? That's how you figure out domain. Algebraically, pretty simple. Just look for the 2 problem areas. Can't take the square root of a negative and cannot divide by 0. Everything else, at least for now, would be fair game. Okay, let's call it there. This was the end of part 1. Looks like it'll be a pretty full day teaching this in class, but I'll find an extra day for us to work in here someplace.